If I tell you that the electric field of this X has a value of 5 newtons for each coulomb, it's that big, and I ask you, how big or how strong is the field at that X, would you answer that it is larger, the same, or smaller than 5 newtons for each coulomb with your clicker? Okay. Remember what an electric field is. It's how hard I would feel a push on 1 coulomb test charge. So what I'm saying is if I put 1 coulomb here, it feels a force of 5 newtons. If I put that same 1 coulomb there, would it feel a force that's bigger than 5 newtons, equal to 5 newtons, or less than 5 newtons? Do you have your answer? Okay. These people are lost. These people are just goofing with me. It's these two groups I want to talk to. Okay? I've divided the class roughly into half, and these two groups are believers and unbelievers, or infidels. Okay? Believers in field lines or unbelievers in field lines? Okay. The believers in field lines. Why did you say that it would be the same?
Equal spacing.
Equal spacing. The spacing tells me how strong or how stinky the field is. If I got the same spacing there, I got the same field. It's got to be exactly the same size. Now you unbelievers are saying to yourself, that's crazy sauce. I mean, it's further away. The further away I get from a source, the weaker the field. Twice as far away is a fourth as strong. If the source is a point source. But this is a new animal. And I'm going to convince you, I hope, I'm going to try 3 different ways. I'm going to convince you that the electric field near a sheet of charge doesn't depend on distance from the sheet. I get exactly the same field there as I get here. Let me try the first way. Whoops. The first way is to say, what if I covered up that positive sheet? You can't see the sheet. What's causing the field lines? Is it a positive sheet down here, or is it a negative sheet up there? What if it's a negative sheet up there? The field lines would have to be going towards on both sides. But if I had a negative sheet causing these fields, wouldn't you want that one bigger? The one that's closer to the sheet? Yeah, you would. So if you don't know what's causing the field, you just say, oh, I guess I don't know which one's bigger. Depends on what's causing it. And if I get the same field lines from both of those charges, I should get the same ranking. Okay, that was my first attempt. Give me 2 more kicks at the can, okay? Now, what we find is that near a plate of charge, or a sheet of charge, the E field does not vary with the distance from the plate. And what we find is that for a single sheet, or a single plate, with charge density sigma, the E field strength is dependent on the sigma, period. I divide by this constant. That epsilon naught is called the permittivity of free space. You'll never need that name unless you go to a geek party, okay? It happens to be 8.85 times 10 to the minus 12 coulomb square over Newton meter squared. Again, you're not going to need that. It'll be on the front page of the exam.
Are we still talking about just when we're right at the surface, microscopic level?
we can use this formula if you're close to the surface compared to the distance to the edge. If it's a meter from here out to the edge, and I'm a centimeter or two from the surface, it will be this value. Okay, so that's the way we use this approximation.
So is it that there's no difference in strength, it's just that the difference in R would be so small that it becomes insignificant?
As long as we're in that regime, yeah. But whether you want to say it's so small that we can't measure it or there's no difference, it's semantics at that point. Yeah.
And you couldn't use it on a larger scale of like the surface of the Earth.
Good. Yeah.
You could?
If I could charge up a surface like the size of this campus, then we could be 100 meters from the as long as that distance is small compared to
A singular charge.
right.
Is there a formula for that ratio?
Yes. If that's L and that's D. I'm looking from the top down and on the side. D would be much less.
There's not
Which is the same as I said with my mouth, which works. Okay, there's that permittivity of free space. Okay, now for point charges, the electric field strength varies drastically with distance. Twice as far as 4 times as weak. Okay, and that K value we've seen before and again and again and again. Now I told you that I was going to take 3 kicks at this can. I've only taken 1 kick. So let me try again. This time, I'm going to take this sheet of charge, and remember this green line is only a line because I'm drawing on a 2-dimensional screen. In real life, it would be a sheet that comes out and just cuts the class in half here, okay? Now, in the past, when we wanted to find the field due to an extended charge, we've broken it up into small bits. Now, in this case, instead of small clumps like peanut butter, I'm going to cut it up into slats, like in a basketball court. This would be a wooden slat that comes out forever and goes in forever. And this would be another wooden slat that comes out forever. And these wooden slats are charged. Now, if I take a little positive test charge, and I put it right here close to the sheet, I can look at the contribution due to several of those slats. Now, first off, these 2 slats here are fairly far away from my test charge. And when they push on the test charge, they're pushing in a direction that's almost opposite. So when I add their contribution, I get a very small contribution. They almost cancel out. On the other hand, if I look at contributions from here and here, I get bigger forces because they're closer and they're pushing in more the same direction. So when I add their contributions, I get a huge contribution. Now here's the game I'm going to play. I'm going to say that the charge within a cone of half angle 45 degrees is going to be the most effective charge for pushing on that test charge. Okay, the charge in here, the charge in this half cone, okay, so if this is my sheet and I've got the charge here, I'd take a half cone 45 degrees in all directions. And there would be a circle of charge that would all be pushing in pretty much the same direction. Okay? Now, if I move that test charge further away from the sheet, 2 things happen. First of all, the charge that's pushing is further away. So the push is weaker for each bit of charge. But the second thing is that if I look at that cone of angle, half angle 45 degrees, the cone that pushes in pretty much the same direction, I get more charge in that cone. Now, it turns out that these two effects cancel each other. By moving this test charge twice as far away, my push by each little bit of charge gets smaller by 4. But also by moving this twice as far away, the amount of charge that's pushing gets bigger by 4. And so suddenly the two effects cancel each other out. See if your neighbor is a believer now, a believer in field lines. Okay. That was the second kick at the can to convince you. Let me try one more time. A little while ago, a friend of mine, Jack Drumheller, passed away. Jack was a professor here in the department, an outstanding teacher, a master teacher. He was also provost of this university for many years. He was also a pilot during World War II. And what he told me was that during World War II, when pilots were shot down over the Pacific, they prayed for bad weather. And this is why. When you're shot down over the ocean, you come down with your parachute. The last thing you want to do is arrive at the water with your parachute attached. Because what's going to happen? It's going to come down on top of you, it's going to get wet, it's going to drag you down, it's going to drown you. So what you want to do is, as you approach the water with your parachute, when you get 15 feet away, unbuckle your parachute, drop the last 15 feet, swim away, and let the parachute land not on you. Here's the problem with a sunny day. With a sunny day, there's no waves. With a sunny day, you look out and you see flat ocean everywhere. When you're 100 feet up, you look out and you see flat ocean everywhere, as far as the eye can see. When you're 15 feet up, you look out and you see flat ocean everywhere you can see, as far as the eye can see. It looks exactly the same at 100 feet as it does at 15 feet. And the problem that they had on sunny days is that pilots would panic, not wanting to be trapped by their parachute, and would release themselves from 100 feet, fall 100 feet and break their legs, and then they can't swim away or at all. And so what they prayed for was a storm where they could see waves, and they could say, hey, I'm about 2 waves high, time to bail out. Okay? Did I convince you? Are 100% of you believers in field lines now? Check that your neighbor is a believer.